Hello everyone, I'm Michael Pickett. Today I'll be presenting the LEO range physical layer design for secure ranging with low Earth orbiting satellites. It's a paper from Ucenic Security 2025. The core problem this paper addresses is a simple one, but it's hard to solve. So essentially, GNSS and GPS satellite navigation systems can be spoofed, and today's receivers don't really have a way to prevent spoofing that can be done from these systems. So this LEO range paper proposes the first provably secure ranging system built off of low Earth orbit satellites. It's not a heuristic fix, but a system with a formal mathematical security guarantee. So over the next 16 slides, I'll walk through the problem, the system design, and the security proof, and the experimental results. Here are the key topics for this presentation. We'll start with the background of why GNSS spoofing is a real problem. Then we'll move into why LEO satellites enable new ways to solve the spoofing issue. From there, we'll go into the security analysis, which includes some of the waveform information and time of arrival and verification. Then next, the implementation and results of the experiment that was done, and finally, the conclusion and any limitations that are brought up here. All right, so again, back to the root problem is GNSS signals can be spoofed. So global navigation satellite systems, which could include the United States' GPS, Global Positioning System, or the Galileo for Europe, GLONASS for Russia, or BeiDou, any satellite navigation constellation essentially work in the same way. So their satellites orbit in a geosynchronous orbit more than 20,000 kilometers away from Earth and continuously broadcast timing signals. So receivers in devices such as your phones or car or vehicles, boats, etc. They always passively listen and pick up uh, the time of arrival from multiple satellites um, and triangulate your position. Ideal amount is typically 10 to 11 different satellites are used. The device receives it, and from that, you're able to triangulate a very accurate position. But the fundamental problem is that the communication is one way. So the device on the ground on Earth just receives information from the satellite in orbit. So because of that, there are two classic attacks. First, the relay attack, which is an attacker can record an authentic GNSS signal in one location and then retransmit it somewhere else. And the issue with this is the receiver or receiving device has no way to tell the difference, and the attacker doesn't even need to break any encryption to do so. So the second issue is that signal spoofing, where an attacker generates entirely fake satellite signals from scratch, basically, can overpower real ones with higher signal strength and can move a victim's perceived location by hundreds of kilometers or more. And one other point is that these aren't just hypothetical situations. There have been real incidents of ships in the Black Sea suddenly appearing to be at airports or drones getting hijacked mid-flight by GPS spoofing, and even cryptographic countermeasures like navigation and message authentication, which cryptographically signs the content of the message. They don't fully close this gap. So because they don't protect the timing of signal, which is what the position depends on. So again, the root cause of GPS signal spoofing, and it's worth remembering that without a return channel, the receiver simply cannot verify when a signal was actually sent. And so that leads us next to the solution that LEO range presents. Low Earth orbit satellites enable more security, and the reason is that they're much closer to Earth, less than 2,000 kilometers away. The signal strength is much stronger, and they communicate bidirectional. So that key difference of bidirectionality unlocks everything else in this paper. If a device can send a signal and get a response, you can measure the round trip time of sending, getting a response, measure the total time, and then divide that by 2, and then you can calculate the distance. So it contrasts with the GNSS of only receiving, with the additional augmentation of adding a low Earth orbit satellite into the equation. You essentially have a form of authentication and a second opinion to verify that the communicated data, such as the location data, is actually correct. Even though LEO satellites communicate bidirectionally, there's a couple engineering challenges to consider. First, the Doppler effect. LEO satellites move at roughly 7.5 kilometers per second relative to the ground, which creates an enormous frequency shift, and the ranging system has to stay accurate throughout the whole process without falling back on GPS for correction, because GPS is what we don't trust initially. Second, it has to use OFDM, which is orthogonal frequency diffusion multiplexing. So instead of sending data over one frequency really fast, OFDM splits it across many frequency lane subcarriers that transmit in parallel at once. So this is already being used in Wi-Fi 802.11 and 4G, 5G communication. So the issue is that the ultra wideband short pulse techniques, which other secure ranging systems rely on, aren't compatible with how these systems already communicate. So implementing them is definitely a challenge. So the third point is that OFDM's long symbol structure is exactly what makes it vulnerable to something called early detect and late commit attacks. So because OFDM symbols take a relatively long time to transmit, an attacker can start transmitting before the real signal even arrives. Watch the real signal as it comes in and adjust their fake signal on the fly to match it. So since OFDM takes a long time to transmit, an attacker could start guessing the signal that is being generated and then adjust it in a real time to perceive as a real signal when in fact it's a false signal. The fourth point is no existing system has a formal security proof against this kind of attacker. So standards like 5G and 802.11 use tricks like phase randomization, but nobody has proven a bound on how well it holds up against truly optimal worst case attacker. And in fact, some recent work has found ways to break the defenses of that. So in summary from these difficult implementations is needing a system within the LEO satellite communication that is Doppler resilient, OFDM compatible, resistant to early detect, late commit attacks, and formally proven to be secure. So that's the goal of this LEO range paper, of achieving all of those goals in one implementation. The LEO range has 5 components. Think of the first 3 as the actual protocol, and the last 2 as proving and validating that the protocol actually worked. So the first one, waveform design. The packet structure combining public timing preamble with an unpredictable OFDM symbol, as I mentioned previously. The second is the time of arrival estimation, which is cross-correlating the received signal against the known preamble to find the correct timing in a way that is Doppler resilient. Third, time of arrival verification. So for each pair of the unpredictable symbols, computing a frequency domain error metric to check whether the packet is actually legitimate. The fourth, the security proof, showing mathematically that the false acceptance rate is bounded by 2 to the negative 20th power against any attacker at the physical layer, not just the ones they happen to test. 5, the hardware validation. So actually building this, testing it out with realistic satellite channel emulation hardware, and not just a simulation. The key idea trying it all together is split every packet into a public part used purely for timing and a secret unpredictable part used purely for verification. So that separation is what makes the whole scheme work, and then we'll get into that in the next few slides of the details. So the LEO range packet design has 2 parts. The first being the public Zadoff2 preamble, which is a special mathematical sequence that is essentially used as a known reference signal at the start of a transmission to accurately measure the time the beginning of the transmission took place. So it produces a sharp, unmistakable peak, making timing precise, and also survives frequency shifts from Doppler effects. So since this is public, everyone knows exactly what it looks like. Its only job is enabling the accurate timing through the cross correlation. They have a consistent amplitude across all subcarriers and good autocorrelation properties, and it's an important part of this LEO range design is that they're Doppler resilient. And this isn't a new concept. It's been known for a while. It's just in the same family used for synchronization and 4G and 5G cellular communication. So this part of the design is pretty mature and well understood. The second part is a series of OFDM symbol pairs whose contents are unpredictable to anyone without a shared secret key. This is where the actual security comes from, and the design choices here are deliberate. So no pilots because pilots are known values that would help an attacker predict the signal. No cyclet prefix, um, again, so there's no predictability. It's predictable structure that becomes an attack surface. So we don't want anything to be cyclic and nothing predictable. Instead, they use a per subcarrier phase randomization derived from a shared key between the device and the satellite. So they organize symbols into differential QPSK pairs, which are a grouping of digital data into 2-bit pairs that are modulated together over a radio or carrier wave in a quadrature phase shift keying, is what QPSK stands for. So it's the fundamental building block of QPSK digital communication. Again, part of the point being is that QPSK splits the data stream into parallel streams, grouping them into pairs so it can transmit 2 bits per symbol. And the first symbol in each pair lets the receiver estimate the current channel conditions, and the second symbol carries the actual verification data. So to summarize, the public preamble for timing, secret unpredictability symbols for verification. That splits the foundation everything else builds on. So the two core algorithms are the time of arrival estimation and the time of arrival verification. The time of arrival estimation is pretty straightforward. It's the cross correlation of the received signal against the knowns out of two amplitude signal. The location of the peak in the correlation is the time of the arrival estimate. And since Doppler just rotates the whole correlation output rather than smearing it, that peak will stay sharp and detectable even at the LEO satellite speeds. The time of arrival verification is a little bit more subtle and happens per symbol pair. So the first symbol, which the receiver also knows independently, and use it to estimate the current channel, which is the H estimate equals to Y1 received divided by Y1 expected. Then that channel estimate is used to predict what the second symbol should look like once it passes through the same channel. So Y2 predicted equals the H estimate times Y2. And then finally, you can square the Y2 received minus the Y2 expected to get the error between what was actually received and what was predicted. If that error is below an adaptively chosen threshold, the pair will pass. So for a legitimate packet, the only source of error is usually just the channel noise, which is small, and is bounded by the signal to noise ratio. But if an attacker running an early detect, late commit attack, they have to guess what the second symbol contains before they actually observe it. So it's unpredictable without the secret key, essentially. Any wrong guess in the time domain gets spread out across every single subcarrier. So once you take the Fourier transform into the frequency domain. So instead of one small error, the attacker's mistake shows up everywhere at once, and the total error explodes well past the threshold. So for the threat model, it deliberately over-approximates the attacker's power, because if you can prove security against an exaggerated attacker, then definitely this will safeguard against a more realistic one. So in this case, the attacker is allowed full control over the wireless medium, free choice of the first symbol in each pair, instant knowledge of the second symbol the moment it's transmitted, zero processing delay, the worst case, and and a perfect noiseless channel straight to the victim. So this setup is extremely strong adversary. But what they can't do is exceed the speed of light, obviously. Um, they cannot know the second symbol before it's transmitted because it's derived from a secret key they don't have. And the attacker's goal specifically is distance reduction. So tricking the receiver into computing a shorter distance than reality by advancing the apparent arrival time. So for reduction, it requires the signal to arrive earlier than physically possible, which is where the attack takes place and the defense needs to live. The timeline at the bottom shows the attack in action with the legitimate transmitter sends the public symbol, then the secret symbol revealed by the sample. The attacker trying to get ahead has to guess their version of the secret symbol before it's revealed, and then can only start adapting the late commit phase once the real data starts coming through. So the gap between where the attacker starts and when the legitimate signal starts is exactly the distance reduction they're attempting. So here in this slide, the delta D is the distance reduction the attacker is trying to fake, basically how much closer they want the victim to believe they are. C is the speed of light, and T advance is the time advance. So this paper's main theoretical contribution comes down to 3 different steps. Step 1 is finding the optimal attacker that show the best possible early detect late commit strategy. So this way you know what to protect against in the most extreme cases. Then step 2 is the adaptive threshold. So instead of using one fixed error threshold for every packet, they set the threshold dynamically based on what the attacker actually sent during the early detect phase. So this closes off a loophole where an attacker can't cleverly choose their early guess to game a static threshold because the threshold adapts to whatever they picked. Then step 3, a sub-Gaussian concentration. So the secret QPSK symbols that are essentially random, plus or minus 1 value in 2 dimensions, is what makes them sub-Gaussian random variables. So using standard concentration inequalities from probability theory, you can show that the probability of each fresh random symbol accidentally lining up with whatever the attacker guessed decays exponentially as you add more symbol pairs. So with 200 OFDM symbols, the false acceptance rate is bounded by 2 to the negative 20th power. So less than 1 in a million against any physical layer attacker attempting any distance reduction beyond the system's proven spoofing radius. And the paper states that it's the first result of its kind for OFDM-based secure ranging. So again, this paper is proving out that their strategy keeps their false acceptance rate basically to 1 in a million. So for their test implementation of the strategy, they used a signal generator as the transmitter, a channel emulator, and a oscilloscope as the receiver. The emulator is the key piece that makes it pretty realistic, as it can reproduce some real orbital dynamic, Doppler shift, and fading data, which is far more realistic than pure software simulation would be. Also, they tested this across 4 different environments of dense urban, urban, suburban, and rural, and both in line of sight and non-line of sight conditions, which make a difference. With the signal to noise ratios ranging from 8.8 decibels at low elevation to 17 decibels at high elevation. And the system itself ran at 2 gigahertz center frequency with 61 megahertz bandwidth, 200 symbols per packet, and roughly 1,800 packets tested per scenario to get a good set of statistically solid numbers. All right, so here are the results from their experimentation. Remember that the false acceptance rate is a fixed at 2 to the negative 20th throughout their experiments. So that's their target value to be under that. So the security guarantee never changes based on any environment. What varies though is the false rejection rate. So how often a perfectly legitimate packet gets wrongly rejected. And the spoofing radius, which is the practical security bound. Essentially the minimum distance reduction an attacker would need to attempt to have any real chance of success. So in the best case, at line of sight and high elevation, which makes the most sense for satellite communication, was 3% false rejection rate, and the spoofing radius was 78 meters. And in the worst case, non-line of sight and low elevation, it was 195 meter spoofing radius at 6% rejection rate. It was also interesting though that the non-line of sight higher elevation has a higher rejection rate than the lower elevation of 9%, which is assumed to be because the multipath reflections at that geometry create more channel variability and trips up some of the channel estimate times. So in relation with classical GNSS spoofing that can relocate a victim by hundreds of kilometers anywhere on Earth, really, the LEO range bounds any successful attack to between the 78 and 195 meters based on their test methodology. So that is drastically way lower than the original one-directional GNSS spoofing. And again, it's demonstrated with their realistic 3GPP channel models on real hardware and not just an idolized simulation. So where does this matter? First of all, essentially by combining the range measurements from 3 or more LEO satellites, you can get verifiable multilateration, and you can prove a device is within a specific geographic region even while under active GNSS spoofing attack. Today, some things to consider are like location-based content restrictions and regional licensing are essentially bypassed with a VPN, but with the LEO range method, this would provide physical layer proof of location that is much, much harder to fake based on their results. And the big point of this is GNSS augmentation. So this is not to replace any GPS satellites. It's essentially to just run the low Earth orbit range alongside it as an independent cross-check. So if the two disagree by more than the spoofing radius, you know that GPS is under attack. And companies like Zana Space Systems and Geely Space are already building commercial products in this wheelhouse. And the last key point of why this matters is that secure time synchronization, such as uses on power grids and 5G base stations, financial systems, all depend on GPS-derived timing today. And that timing is spoofable, as we discussed with the current GNSS satellites. The LEO range gives them an independent, much harder to attack timing source that is much more reliable. So some of the limitations and open-ended questions. Firstly, the non-line of sight performance is the main pain point here, and how the geographical features of the Earth that essentially block you from line of sight to satellites are more harder to distinguish from an actual attack. The 5G bandwidth is also somewhat of a limitation too. So the current standards cap the bandwidth at 100 megahertz, and the spoofing radius is inversely related to bandwidth. So the more spectrum in the future could shrink the radius even more. And lastly, the distance enlargement. It can never be fully prevented with a single range measurement since an attacker can always delay a signal. So solving that would require multiple independent LEO satellites for that verifiable multilateration and not just a single link to a satellite. So a few points of comparison on how the LEO range method compares to some of the other IEEE standards that we currently have is you can see across the board when comparing OFDM and security proof, LEO communication, and Doppler effect, that the LEO range methodology checks all the boxes across the board, and some of the other methods only cover one or two. So, in summary, LEO range is a novel OFDM native physical layer design that would be compatible with systems like 5G, NTN, and Starlink, with no additional specialized hardware that's required. It comes with the first formal security proof for OFDM-based ranging, and a false acceptance rate bounded by 2 to the negative 20th against any optimal physical layer attack. And furthermore, it uses a clever frequency domain verification scheme that's inherently robust to Doppler, which is a key pain point for bidirectional satellite communication. Also, by their experimentation, has been validated on real hardware, achieving that 3 to 9% false rejection rates while bounded under any spoofing attempt to under 200 meters. So a big takeaway from this is that the more LEO satellite constellations that are being deployed into space right now, if secure ranging isn't built in from the start, then there will still be more and more risk with the same mistakes that GPS or GNSS has made with these inherent spoofing vulnerabilities. And that building in this methodology, the LEO range shows that a provably secure alternative is both achievable and practical in GPS related applications.